Okay, these worked examples are going to be demonstrating differentiation of composite functions. So if h of x is a composite function f of g of x, then the derived function h dash of x, we have to differentiate the outside function, so it's f dash, leaving g of x alone, f dash of g of x, and then multiply by g dash of x. Now I'll just do a couple of simple examples for you, highlighting some of the techniques and skills that you need to use in these examples. So if f of x is equal to 3x squared minus 5x all to the power of 7, to differentiate this, we don't want to have to expand out this bracket, so that's where our composite functions become very useful. So f dash of x, we need to identify the inside function and the outside function. The inside function is within this bracket, x squared minus 5x. The outside function is the 3x to the power of 7. So differentiating that to the power of 7, we have 3 7s are 21, leaving the x squared minus 5x, the inside function, alone. So we've got 21 x squared minus 5x all to the power of 6. Then we have to multiply by the derivative of that inside function. And because it's going to have two parts, I'm going to bracket it. It's 2x minus 5, and those brackets are very important. We can leave it like that. There's no need to simplify it any further. Any sort of rearrangement we might do is bring the smaller power to the front and the larger power to the other side. A second type of equation here, if f of x is equal to 1 over 5x minus 2, our composite functions here, we've got 5x minus 2 as the inside function, and the outside function is the 1 over x. Now, from what we did with polynomials, we can't differentiate it as it stands here, so we need to rewrite this as 5x minus 2 to the negative 1. Now we can actually find the derivative. So f dash of x, doing the outside function first, which is the power of negative 1, is negative 5x minus 2 to the negative 2, and then multiply by the derivative of what's inside, the inside function, which is 5. Tidying this up, I would write it as minus 5, 5x minus 2 to the minus 2, or I could return it to positive indices, which would be 5x minus 2 all squared. A third type of example that you might meet is with our square roots. So we've got x squared, square root of x squared minus 4, and again we can't differentiate it as it stands, we need to alter it. So this is x squared minus 4 to the power of a half. F dash of x, we have to differentiate the outside function first, so it's a half x squared minus 4 to the negative a half, and then multiply by the derivative of what's inside the bracket, the inside function, which is 2x. We can simplify this, that half and the 2 cancels out, bring the x to the front, x squared minus 4 to the negative a half. We can return it to the form that it was given to us in by bringing the negative a half power to the denominator and putting it back as a square root. It's not essential, but depending on what you're going to do with it from here, You may leave it in this form or alter it. So those are just some of the types of examples that you're going to meet in terms of differentiating composite functions. You've got your standard one where you've got the power as the outside function and inside the bracket as the inside function. Then you've got your quotients that you have to use your negative indices for, and your square roots which you have to use your fractional indices for before you can actually differentiate them.